Hello everyone. I wanted to discuss a very important topic today: statistics. Life surrounds us in its expanse, and through repeated events we can derive meaning. Scientists have made it their goal to observe their surroundings, and in this pursuit, scientists gaze upward at the stars. They made rockets that took mankind into space, but unfortunately, in 1986, there was an event known as the Challenger Space Shuttle disaster, where 7 astronauts gave their lives when their shuttles exploded shortly after taking off. This was caused by a variety of things, but one of the main potential culprits was a component known as the O-ring failing. It had been later determined that the O-ring had a critical flaw of temperature sensitivity that had been missed by the scientists, because upon reviewing the data set on their launches, they had only looked at launches where the component had failed, and this alone wasn't enough to show any trends or potential causes. I'd like to show you how statistics could have been used to determine the cause of this failure, so mistakes like this don't have to happen again. I'll be using Python and TensorFlow probability to show you how Bayesian statistics can determine trends and predict events. A link to this notebook can be found in the description if you'd like to run the code for yourself. Make sure to use the proper version of TensorFlow and NumPy for this to work. Here is the dataset that was collected of defective O-rings plotted against ambient temperature at the time of launch. Pairing the data together, it's easy to see that as the temperature decreases, the chances of defects increases. But it's not exactly clear how this probability might behave. So a good way to determine that is to take a function that could model its probability and parameterize it. Here, the logistic function would work well because the probability starts close to 1 and drops to 0 as temperature would increase. And beta can tell us about the rate of change of this probability, where we can have a rapid change, gradual change, or inverse if beta is negative. However, if we want to plot our probability with the center not at 0, we need to add a second parameter, alpha. When we add alpha, we can see that the center for these shifts over to the right for different values of alpha and to the left for positive ones. Now, we don't know much about these parameters beta and alpha. They can be positive, negative, or really large, so it's best to use a normal random variable to consider what they might be. A normally distributed variable is most likely to be centered around a mean with a precision. Here, the mean is represented by mu, and the precision is represented by tau. And if we have a high mu value, it's centered over here, or if it's negative, it'll be centered here. And tau will tell us how precise it is, where a high precision has a tight bound here, and a small tau gives us a wide spread. Now that we have this, we can start to parameterize our function. And in order to do that, we will be considering a Bernoulli random variable, where Bernoulli random variables have a specific probability of being 1 or 0, where 1 is defect and 0 is no defect. After running this model, which goes into more detail in the notebook, we can see that our posterior distributions of our variables, beta clusters around a non-zero value, which is good. This implies that our model would indeed depend on a temperature, where if beta was 0, we would not have any change in probability. Here we also see that alpha is clustering around a negative value to show that the graph is shifted over towards the temperature that we're going to be looking at. Now with these posterior values, we can plot the average probability that we have determined here by the blue line, and here shown are two other examples of possible beta and alpha values, but these are equally as likely as each other. This is merely just the average. If we want to be certain about our results, we need to include a confidence interval. Pictured here is a confidence interval of 95%. Looking at 65, we can be 95% sure that the probability of failure is somewhere between 0.3 and 0.8. But as you can see, our lack of data here allows a large amount of probability on the left-hand side of the graph rather than the right-hand side, where the bound is much tighter. This is why it is important to look at more than just your average value of probability, because there's a good chance that the real probability might lie somewhere else. With all being said, we can now look at the chances of failure given the conditions at the launch. And on that day, it had been 32 degrees Fahrenheit. Using our model's distribution, this gives us an extremely high chance of failure in our distribution of probability. But there's more that can be said. The way we tested this, we picked the logistic function, and you might want to ask, how good is this function? So we need a goodness of fit. Another example of a probability distribution is to say 100% chance, and while that would be accurate, it is not a good model for our situation. One way to test this goodness of fit would be to simulate more data points and check if those simulated data points fit our model. The notebook goes into more details on how they have done that, so you can look into that yourself if you'd like. And using their methods, here are 4 generated sample datas. All of them are slightly different from each other, and all are much like what the data set that they currently have looks like. Applying our model to this data set, sorting it, and displaying it, we can see that as the probability of detecting a defect increases, we actually do see more defects. No model is perfect, and that's why we can see some blue values outside of this line over here, showing that even though we have a good model, this isn't perfect. To compare, a perfect model would have it guessing the values 100% of the time. A random model has defects occurring randomly, regardless of our probability, and a constant prediction has the average chance that an event will occur overall, and we can see no correlations. But our model clearly shows that it definitely is a good fit. With everything presented here, this model is just one of the many ways statistics can help us determine events. In this case, it can help us discover potential dangers present in a system and can be used for other phenomena or events that may happen. It is paramount that scientists and those alike rigorously test their systems, especially through the lens of statistics shown here. It's a tragedy that the Challenger disaster happened, and from this, we can learn how to do better and prevent things like this from happening. Together, we can make the future of progress safer for everybody. I'd like to thank you for taking the time to watch, and I'd like to thank the astronauts for their service. Have a good day.